In this lesson, we will look at the statistical test that tests for different means. The scenario is the following. You are given two sample datasets, and you compute the mean of each dataset and take the difference. Now the question is, does this difference in sample means allow you to conclude that there is a similar difference in the underlying populations? Now, this is indeed the exact scenario that we used when we went through the entire reasoning of statistical testing a few lessons ago. And in fact, this is the most used test in all of statistical testing. Some examples are A/B testing, for instance, measuring the difference of website traffic on different web pages, or policy changes, or also ad campaigns. Which ad gives us the highest conversion rate? Now, these are all examples where you would want to apply these tests. To test for equal means, there are in fact several different tests, each only valid in its own scenario. And each different test comes with different requirements. We have already encountered one type of requirement, namely that revolving on the underlying statistics of the datasets. You could require normalcy or equal variances. But there is another type of requirements that are more about the context of the underlying data. And this requirement introduces the distinction between independent data and paired data. So let's now first look into this distinction. Let's first look at independent data. And instead of giving you a general vague definition, let's look at some scenarios that will produce independent populations. Let's say, for instance, that you're looking at the difference in testing between two universities. One university perhaps focuses more on homework assignments, whereas the other focuses all its attention to the final exams. Now, your task is to look at the performance between the students of these two universities. Now, these are clearly independent samples because not one student will be in the two samples, because most naturally, students only go to one university. So these are independent samples. The second example comes from the medical world. Let's say that they want to test the effectiveness of a new drug. Now, what they will usually do is they will hire two groups of people. One group they give the new drug, and the other group they will give a placebo, so basically something without any active substance. Then at the end of the trial, they will compare the success rates between these two groups. Now, this procedure again produces independent populations, because no one person is part of the two groups simultaneously. We just look at two independent groups and keep them separated throughout the entire trial. The third example is, for instance, looking at the difference in income between males and females in the same industry. Again, two independent samples, because no person can be both a male and a female at the same time. So these two groups are kept separate at all times. And this is what it means to be independent populations. And in the course notes, you will find some more examples. Now, independent populations are, of course, the opposite of paired populations. Now, in paired populations, we have the same group of test subjects going through different scenarios. And thus, there is a large correlation between these different scenarios. Let's look at some examples. Before and after studies are a clear example of a paired dataset, because we have the same group and we look at them before an event happening and after an event happening. Or another example is that we take a different test but in the same class. So we have the same population set, the same group of people. We first let them take one test and then we let them take another test. And we see whether there is a difference in testing score between the different types of tests. Another example is to look at employee performance before and after a bonus scheme. So we again have two data sets, employee performance before the scheme and employee performance after the scheme. So two data sets, but they are not independent. They are paired because the underlying test subjects are the same. Now we don't have to work with people. For instance, we can look at the battery lifespan before and after a software update. Now, why is this paired? Because we're looking at the same battery. The only thing that changed is the scenario or the environment in which it finds itself. So from these examples, The difference between independent datasets and paired datasets should be clear. But why would we make this distinction in the first place? Well, because for paired populations, there is a clear correlation that will be present in our datasets. So if we are then, for instance, looking at the mean of these two datasets, if there is a clear correlation between them, then this needs to be taken into account. And that is why there will be different statistical tests for paired data compared to independent data. So let's now look at which statistical test to use depending on which requirements are fulfilled. So let's say that the following requirements are fulfilled. For instance, we have normalcy, meaning that we know that our samples are drawn from an underlying population that is itself normally distributed. In addition to that, we have equal variances. So the underlying populations of our samples are likely to have equal variances. In this case, we have two scenarios. We either have samples coming from independent datasets, and then we will use the test, the independent student t-test. And that is also the test that we used in the previous lessons when we looked at the reasoning of statistical testing. However, we can also have a paired dataset, and in that case, we will use a paired student t-test. Now, if we don't have equal variances fulfilled as a requirement, but we do have normalcy, so we have a dataset with normalcy but unequal variances, then because we have unequal variances, we assume that the underlying dataset is an independent dataset. And in that case, we will use the Welsh t-test. Now, these are three different tests that are valid in their own specific scenario. But in Python code, each test will of course correspond to only one line of code. And to know which specific test will be valid for your dataset, we go through a couple of steps that will get you to the right result. Step 1 is that you check for normalcy, because each of these tests for the equal means included the requirement for normalcy. Now, luckily, we can test normalcy with the Shapiro-Wilk test, but also with the QQ plot and the corresponding R value. So there are plenty of ways to check for normalcy. The second step, if normalcy is fulfilled, we check for equal variances. And this can of course be easily done by using Levene's test. Then if we do have equal variances, we either use the independent student t-test or the paired student t-test. And if we have unequal variances, then we use the independent Welsh t-test. And to see how this works in practice, let's go to our notebook. The first step that we always do is of course that we define our populations. In this case, we take two populations which are both normally distributed. So normalcy will be fulfilled. But of course, you see that I commented a line here with a uniform distribution, just for you to play around with, which we will also do at the end of this lesson. Because we're looking at equal means, I put the means explicitly not equal of these two populations. Then we create our samples. In this case, we take a sample size of 40 data points, and then we compute our sample means. Now, in this lesson, we won't be plotting all that much. The only thing that we will plot is the histogram of sample 1 and the histogram of sample 2, and also a box plot just because we can. It doesn't really add that much to this. The interesting thing is where we actually perform the tests, and we will go through the steps again that we had in our slide. The first requirement that needs to be fulfilled for all of the tests for equal means is normalcy, but that we can very easily check by just doing the Shapiro-Wilk test on sample 1 and also on sample 2. But we can also check our normalcy by using the QQ plot. But in this case, we won't be plotting the QQ plot, but instead we'll only look at the corresponding R² value. And these are abstracted in the same way as before. So we get R² for sample 1 and R² for sample 2. And we print them together, both the p-value of our Shapiro-Wilk test, which is this one, and the R² that corresponds with the QQ plot, which we do here. And we do this for sample 1 and sample 2. And this will give us an idea whether our samples come from underlying populations that are normally distributed. Now, the second step is to determine whether these samples are likely to come from underlying populations with either equal variances or unequal variances. Now this can be very easily done by just performing the Levene's test. So we do stats.levene, sample1, sample2, and we abstract the p-value. And also this value we simply print out on our screen. Now then we have some different possibilities. If they are indeed equal, corresponding to a p-value of the Levene's test that is larger than 0.05, then we take the independent t-test. And this is very easily done again by just using stats.t-test independent from sample1, sample2, and we put equal variances to true. And then the particular p-value of this test we can again abstract by looking at the element at index 1. And we can print this result. So the student independent t-test p-value for equal variances is this value right here. Now, if the Levene's test fails, on the other hand, so if we get a p-value here that is smaller than 0.05, then we will use the Welsh t-test. This will simply be stats.t-test independent, the same as before, but now we put equal variance to false. And it's as easy as that to switch between these two tests. Now, of course, these two tests are for independent samples. Now, what if we have a paired sample? And this was only valid if we had equal variances. So again, when this p-value is large enough, then we just put stats.t-test rel instead of int, and we just put sample1 and sample2. And this we also print. So if we run this cell and we scroll down, then we will see all of our output. So in this specific run, we have a mean of sample1 of 0.111, a mean of sample2 of 1.233, and thus a difference of minus 1.122. And then beneath our plots, we see all of our print statements, which show the result of all of our statistical tests. So we have the Shapiro-Wilk test for sample1, which tested for normalcy, and we see that it has a p-value of 0.588, so quite large, so this will probably be coming from a normal distribution. And the r-squared value is also large, so 0.97. Then for sample2, we can do the same, and we also get values that indicate that also sample2 comes from a normal distribution. And of course, we, as data generators, we know that this is true because we generated the populations as being normally distributed. So this checks out. So then we look at the result of the Levene's test. We see that the p-value is small, but still larger than 0.05. And therefore, this means that we cannot reject the null hypothesis and conclude that the underlying populations from which our samples are drawn do indeed have equal variances. Because we found from the Levene's test that our underlying populations are likely to have equal variances, there are two tests for equal means that are still valid. Either the student independent t-test with equal variance, or the student paired t-test with equal variance. So it depends on the context of your actual underlying data. However, in both cases, the p-value is 0, and this very clearly allows us to conclude confidently that the underlying populations of our samples do indeed have different means. And it is this train of statistical analysis that you will always need to follow if you're given two samples and are asked whether the underlying populations have equal means or not. Now let's look at some more examples by going back to the slides. In this first example, we also see that our two samples are likely to come from underlying normal distributions. Both the p-values and the r-squared are very high. Then in this case, the Levene's test p-value, which tests for equal variances of the underlying populations, is also incredibly large, and thus we conclude that there will be equal variances. And thus, this is the same as we just saw in our notebook. The valid test will be the student independent t-test with equal variance or the paired t-test with equal variance. But let's now look at an example where the variances are not equal. In this case, we again have that the p-value for the Shapiro-Wilk test is very large, and thus normalcy is fulfilled. But the Levene's test p-value in this case is 0.03, so lower than our statistical significance level. And therefore, we can conclude that the variance of the underlying populations are in fact not equal to each other. And we could see this already on the population histograms, because we can see that the blue histograms, or the blue bars, are spread out much wider than the green ones. The only valid test to test whether we have equal means or not is this middle one, the student independent t-test with unequal variance. But this is also 0, so we conclude that the underlying populations again do not have equal means. Let's now look at a last example where we in fact made the populations so that they do have equal means. First, we observe that the test for normalcy, the Shapiro-Wilk test, is indeed successful. Both samples are likely to come from a normal population. However, sample 2 just barely passes the test. Its p-value is 0.08, but it passes the test nonetheless. Then we see from the Levine's test that the underlying populations do not have equal variances. And therefore, the only valid test to test for equal means is the middle one again, the student independent t-test with unequal variances. And now we see a p-value that is not only different from 0, but also quite large. And thus, we cannot reject the null hypothesis, and we have to accept it, meaning the assumption that the underlying populations have equal means. And thus we can confidently conclude that this is indeed the case. Now there is one more scenario that I also want to show you. Remember that this normalcy always has to be fulfilled. But what if we now put population 2 not as a normal distribution, but as a uniform distribution between 0 and 1? And this means, of course, that the mean is 0.5. Now, what if we run this cell and look at the results? We see in this case that our first requirement is not fulfilled. Namely, our Shapiro-Wilk test for normalcy on population 2 fails, because our p-value is lower than 0.05. Now, because this requirement is not satisfied, these tests will not be valid. And indeed, because we see that each of these tests has a larger p-value than 0.05. And this means that we cannot reject the null hypothesis, from which we should conclude that the underlying populations indeed have equal means. But this is clearly not the case. Our normal distribution, or population 1, has a mean of 0, whereas our population 2 has a mean of 0.5. And that's why we see that if these requirements are not fulfilled, then the corresponding statistical tests are not valid and should not be trusted. Now, before we conclude this lesson, a short word on yet another statistical test that tests equal means, namely the z-test. But the z-test falls within the same category as the f-test. Even though it can be very precise, it has such strict requirements that it's almost not usable in real-life scenarios. Namely, the accuracy of the z-test is very dependent on a very large sample size, more than 30, but the larger the better. But also, it assumes to have a very good approximation for the population variances, not the sample variances, the population variances. And most of the times, this information is just not available. And therefore, I would not advise using the z-test in real-life applications. And therefore, it's also not worth going into more detail about this test, because we already have some very robust tests that test the difference in means of our underlying populations. Now, just at the close of this lesson, you might raise the objection that you want to compare the mean not between 2 datasets, but between more datasets. So how would you approach this one? But to do that, we will of course need to go to the next lesson.